All right, so I believe today is the final lecture. And the first thing is basically log structure file systems. So we talked about a simplified FFS, which was very basic, works, but it's not very efficient. So we're going to study something a little bit more advanced. Now, the motivation is actually covered quite nicely by Hyunjung. So I'm just going to skip this. So if we can build an ideal file system, how would it look like, right? So obviously, it needs to have a very good write performance, right? As we saw in the motivation, there's way more writes because you get larger memory, more stuff in the cache that we can read. Now, also there's more bandwidth on the disk, so if we could take advantage of it, that'd be nice. Now, also, we have to understand what are some of the common workloads, right? What are the, depending on the application, what's the usage behavior? So you could kind of customize based upon that. That's also a good system. And since RAIDs are quite popular, it needs to go hand in hand with that kind of system. So what LFS does is that when it's time to write to a disk, first, it's gonna buffer them and in an in-memory segment. So here we're gonna use a term segment. It's basically large space. You don't want to do multiple writes, so it's almost like you just want to buffer it a little bit and just write it at once. So when that segment is full, it is going to be written to disk in a one long sequential transfer to an unused part of the disk. Now, what LFS does here is that it never overwrites, but rather always writes segments to free locations. Now, because segments we talked about is large, the disk is used efficiently and the performance gets much better. So writing to disk sequentially and also effectively. Now, if we think about, how about if we just write sequentially one after another, right? But when we write, there's also other stuff that we need to write, like metadata. And sometimes these sequential writes, although sequential, might not happen immediately right after. And at that time, the disk might have rotated, right? So that you could actually miss. And for the sequential write, you might actually have to wait a little bit. So what we actually want is a large number of contiguous writes or, one big, large write. So that's why, as mentioned, we're going to use something called write buffering. So LFS will keep track of updates in memory. And when it has received a sufficient number of updates, it writes them, which is a segment, to the disk all at once. So here's an example. Now, let's say we have two set of updates. So the first would be 4 blocks, right? These are basically file J, right? So we have an inode for this. For the block 0, it's in A0. So these are 4 blocks plus an inode. Now the second one just has 1 block, which is okay. This is to file K. So we have 7 blocks, which form a segment, and we just write it at once. So it's really common sense, right? Think about it. Like, let's say, same thing. If you want to go to a market right in front of your home, you go get a chocolate, come back. You go get a coffee, you come back. You go get a cookie, you come back. It's not efficient, right? You wait until you have stuff to buy, right? Unless you're ordering from Coupang, right? So again, think about systems. These are common sense. So write until you have a big segment. So then obviously the question is, how much should we buffer, right? How long to wait? So just to put this into equation, let's first say T sub position is the time it takes for rotation and seek for each, right? R sub peak is the disk transfer rate, the peak rate. And the time to write D megabytes of data, T write, will be, you have a positional delay plus D divided by R peak, right? Time to transfer plus time to rotate. Now, the effective rate of writing would basically be D divided by T sub write, and we'll take this equation in here. Now, we want the effective rate to be some fraction of the actual peak rate, and obviously the F, the higher the better, and a typical F could be like 0.9. So here, R effective, this term is basically same as F times R sub peak. Continuing on, easy math, right? So the bottom line in the end, we're going to get D is F divided by 1 minus F times R sub peak times positional delay. So if with that, using an example, let's say we have a disk that has a positioning time of 10 millisecond, peak transfer rate of 100 megabits per second, and let's say F is 0.9, you put these numbers in this equation, you're going to get about 9 megabytes. So that'll be your segment size. Now, one of the challenge here could be actually finding an inode. The reason could be inodes are now scattered throughout the disk. It's not in a fixed location because there's no overwriting. So the inodes actually might keep moving around, right? So this is dynamic. So we need a way to keep track of where inodes are. So for that, we use something called IMAP. Sounds like a map developed by Apple, but no, it's actually inode map. So this actually gives you a level in direction between inode numbers and inodes. And we're going to come back to this later, seeing why this is actually useful. Now, anyways, what this does is that it will take an inode number as an input and then produce the disk address of the most recent version of the inode. Most recent, so the one we're actually interested in. This would often be implemented in an array with about 4 bytes per entry, which is basically a pointer. And anytime an inode is written to a disk, right, IMAP is updated with this new location. Okay, this basically has, this is a map of inode number and its actual location. So here IMAP needs to be written to disk, right? This is to be persistent. Then where should we put this, right? So what actually happens is that LFS places chunks of the inode map right next to where it is writing all other new information. So when here appending a data block to file K, LFS writes a new data block, inode, and a inode map all together onto the disk. So here you first go to IMAP. It shows you that file K's inode is in A1. So you go to A1, which is inode of K, and this also indicates the actual data is in A0. You kind of piece them together. Now, you might wonder, hey, did you just say inode is moving around, scattered, and your solution is an IMAP? But doesn't this also move around, right? Now, that's why you need something that's fixed, right? You're gonna need to have something that's fixed in the end, right? And that's where the checkpoint region comes in. So the checkpoint region would contain pointers to the latest piece of the inode map, right? So this is fixed. And this would have the information of where that inode map is. Then again, that points to the inode, which points to data. Now this checkpoint region also needs to be updated, but we don't do it as often. It's usually do it about every 30 seconds. Thus performance doesn't suffer that much. Now then one might wonder, well, during those 30 seconds, what happens if it crashes? Of course that can happen, and we'll talk about that a little later. So with that, let's just do a recap. Let's say we want to read a file from a disk. And assume that initially we have nothing in memory. So first you go to the checkpoint region, because that contains pointers to the entire inode map. Then it reads the map, and let's cache it, because you're probably going to need this often, right? Because like I said, initially it was blank, right? Nothing in memory. So let's cache that. And then when given an inode number, it will look up the translation, right? The inode number to the disk address in the IMAP and reads the most recent version of the inode, right? So you go to a checkpoint that tells you where the IMAP is, and IMAP tells you where the inode is. And then you read a block from the file, using whatever pointer necessary. So that's reading a file. But we also know we have directories. All right, so we need to talk about that. But if you think about it, directory is just a collection of name and inode number mappings. So when we're creating a file on a disk, for the directory, LFS also writes a new inode, some data that corresponds to the directory data. So here, let's say IMAP has something for file K in the directory, right? So it will say, well, directory is the inode for the directory is an A3, so it has a pointer to here. And this IMAP task says the actual directory is an A2, so you go here, right? So here it looks like has foo in it. Now then you could do another read on the map. It says file K, inode is A1. So you have a pointer here. You look at it, the inode says data is an A0, right? Yeah, so the below here is basically what we just talked about. So if you're trying to access a file in a directory, you go into the directory that tells you first where the directory is and then where the file is. Now, when we have this directory, you could suffer from something called a recursive update problem. So when an inode is updated, its location on disk changes, right? Because we don't overwrite. So if we hadn't been careful, meaning this would have entailed an update of the directory that points to this file, which then would have mandated a change to the parent of that directory, and so on until the way up to the file system, right? The change would just keep going. It's recursive. That's too many, right? So, however, because we have an inode map, we had an indirection here, we can avoid this problem, right? So although the location of an inode might change, this change is never reflected in the directory itself. Now, IMAP structure is updated while the directory holds the same name to inode number map, right? So because we have that map, we don't need to have these recursive updates. Now, LFS, although quite nice, has issues, right? There's no perfect system, and one of them being garbage collection. You guys heard of garbage collection? Like in programming? No? Do you guys collect garbage? You don't collect, but you have, I mean, if you live, there's garbage, right? You put it in a trash, right? You don't? You don't do it. Do you live with your parents? What's going on? You need to clean up your garbage, right? Clean your mess, right? So now, let's say initially we had this data in an inode. Let's say something updated, so we switch to a new position, right? Somewhere new available. Obviously, IMAP would have updated version, but now we're here. This stuff is an outdated data that we don't need, but it's still taking up space. And we call this garbage, right? We need to collect this garbage so that we can reuse it. Otherwise, we're not being very efficient, right? So collecting stuff that's not being used or not recent, not needed, so that we can use it in a better way is a garbage collection. Now, also the issue is because we're kind of moving around and scatter things around, garbage is also scattered around, right? So you need to go collect all these stuff. Now, one way to do this is a versioning system, right? I don't know if you guys use checking in a file, checking out, there's a version. You know, if you check out a file, somebody else cannot check out, that kind of stuff. So nice thing about this is that it keeps older version around in case I need to restore it, right? They say I wrote a wonderful code, and my project mate checked it out and screwed things up, and now it has full of bugs, right? One, you go find your partner and kill that person. I'm sorry, I shouldn't do it. But second of all, hopefully you can go back to the previous version, right? Have you done this before? Yes, Subin has. Where's your project partner now? Yeah. We were talking about Hon and Jim?
No, I have a project with them right now. I didn't go back to find it.
Oh, they didn't screw up your code? I thought you meant. Okay, because you nodded when I said.
Just in my under.
So I'm talking about them, your undergraduate partners. Where are they?
Now?
Yeah.
They are working.
How are the companies doing? Okay, it's good to know. Thank you very much. Yes, Subin giving me life lessons. Yes. So anyways, so this is actually useful sometimes. Versioning system, right? I can go back. Or I could be making a mistake in my own code. I might drink a little bit at night and I wrote code and there's a bunch of full bugs. In the morning, I don't know what happened. Then I might have to go back, right? It's great. Although by keeping all these possible garbage, but here the assumption is sometimes garbage could be gold. But most of the time, garbage isn't. So LFS doesn't do this. Sorry for wasting a lot of time talking about versioning, but LFS doesn't do this. Instead, it keeps only the latest live version, only the most recent one, the one that's we're using now, right? Thus, in the background, it goes around and periodically finds these dead versions and cleans them, right? So garbage collection again, automatically, right? It doesn't ask you to do manually. You know which one tells you to do this manually? You have done it before. Manually collect garbage. You have done it before, trust me. Where? Which language? Which course? 점프구, yes. In C, you have to go do this yourself. You have to free memory, right? That's garbage collection in a way, right? Otherwise, there's a memory leak. And you might have actually learned, I don't know how many of you actually program in Java. Java actually does it for you. Pretty cool, right? It's damn slow because of that, right? So anyways, automatically free unused memory for programs. Now, garbage collection, there's many different issues and there's nonsense papers on garbage collection. Like you just go collect each block, right? Or here in LFS, you could do it in a segment by segment basis, right? When I collect, I want to do it in a segment level. So here's the details. Periodically, the LFS cleaner reads in a number of old segments, and all could be partially used. Because if all the blocks in the segment are old, that's the best case. In reality, probably not. So only some of them. Now, then you need to determine which blocks are live within these segments. And we'll talk about how we know which ones are live or not a little later. Then you write out a new set of segments with just the live blocks. And then you free the old ones. So, in other words, the cleaner would read in M existing segments. Some of them might be old, some of them might be live. You compact their contents into N new segments. And then write the N segments to the disk in new location. So whatever live, whatever we still need, right? Let's say we have a big block, only one portion is being lively used, then you could actually decide to, okay, I'm gonna rewrite this thing that we need somewhere else so that I can just free these up. Yes. So how do we decide whether this block is live, right? Because you don't wanna make a mistake here. So given a data block D within an on-disk segment S, LFS must determine whether D is live. So LFS includes for each data block D its inode number, which file it belongs to, right? And its offset, which block of the file this is. This information is recorded in a structure at the head of the segment known as a segment summary block. So for each segment, there's a little bit of overhead, right? I'm gonna put it at the top, like a header, saying, hey, this is a summary. So for block D, located on disk at address A. This is actually the summary. You look in the segment summary block and find this inode number, N, and offset T. And then you look in the IMAP to find where N lives and read N from disk or memory, wherever it is. Finally, you use that offset T, look in the inode to see where the inode thinks the teeth block of this file is on disk. Right? So you're tracking what inode tells you for that. If it points to this address A, then block D is live. So just making sure the information here is actually legit, then you know this is live. If it's pointing to somewhere else, then that's garbage, right? Nobody's using it. There's no pointer to it. There's nothing pointing to it, then that's garbage, right? So again, common sense. So with that, how often should we clean? The answer is, okay, not too often, but periodically, possibly at idle time, or when your disk is full, right? It's a very good time to collect garbage. In terms of which blocks, well, you could actually categorize segment into hot or cold. Hot segment could be, this is frequently overwritten, meaning this is a hot part where there's a lot of read writes going on here. So possibly we don't want to collect this, right? Versus this is relatively stable, it hasn't been changed for a while, then probably better to collect them more often. All right. Mentioned about crash recovery. So LFS buffers the writes into a segment and then writes the segment to disk. Now, LFS organized these writes in a log, right? That's basically a buffering process. The checkpoint region points to a head and tail segment. And each segment points to the next segment to be written. LFS also periodically updates the checkpoint region. Now, crashes could happen in both of these operations, right? One, when you're periodically updating the checkpoint region versus when you're actually, writing these in a log. So we're first going to look into this case and then jump ahead to the other case. So to ensure the checkpoint region update is atomic, LFS keeps two checkpoint regions, one at the either end of the disk, and you write to them alternatively. And when you're updating the CR, it first writes out a header, and importantly with a timestamp. Then the body of the CR, and then finally one last block, also with a timestamp. Now, let's say the system crashed during this update. LFS can detect this by seeing an inconsistent pair of timestamps. Okay, so at least you detect it crashed. And then it will choose the most recent CR that has consistent timestamps. Basically, you revert. That was the one that I have that's actually correct. So you go back there and then you resume. For the other case, like, so let's say there was a crash during this process. Then let's say we reboot. Then LFS can recover by reading the checkpoint region, the IMAP piece it points to, and subsequent files and directories. But remember, these checkpoint updates are around 30 seconds, right? So whatever you did in between is all lost, which sucks, right? What if that's like 29 seconds ago? So in that case, you're going to use something called roll forward. So you start with the last checkpoint region, you find the end of the log, and use that to read through the next segments and see if there are any valid updates within. So basically the same thing. You go to the last legitimate CR that you have, you kind of go forward and see if there's anything we can salvage. So if there are, LFS updates the file system accordingly and thus recover much of the data and metadata written since the last check. Again, you do it, possibly there's nothing, but at least you try. So that's all they do for crash recovery.